Hello dear friends, welcome to my channels. Today's discussion is group theory. So let E be a prime. Determine the number of homomorphism from ZP plus ZP into ZP. Let I such that ZP tends to ZP a homomorphism. Phi A, comma B equals to A high 1, 0 plus E high 0, 1. Determine a number of we only need to know a number to determine the number of homomorphism we only choices for high 1, 0 and 0, 1. But P is prime, so we can each this element in ZP everything 0 will be a generator, so the image will automatically have order p or 1 or 1. Thus the number of homomorphism equals to p square. So my answer is set phi is from Z30 and onto a group of order 5. Determine that since phi onto a group order 5, the order of the kernel is 30 divided by 5 equals to 6. Means kernel order of kernel is 6. So kernel be order 6 subgroup of Z30, namely 5, 10, 15, 20, 25, 0. Homomorphisms are there Z20 onto Z2ZE. Notice the difference between the first and question is now image of I is A in order of the image must be the order of Z, since order of Z20 equals to image phi, order of image phi into kernel, but it does not write 20, so onto homomorphism between Z20 and ZA. This is marking onto. And now question is Z22. Now consider homomorphism in general form Z20 to ZA. The order 1 must divide 8 and 20, or the GCD 8, 20 equals to 4. Thus, the phi 1 has ordered map if the image is 2460 ix equal to 2x or phi x equals to 6x. Hence, there are the homomorphism to Z. Now we are going to solve question number 4. Suppose that phi z5 50 50 to z15 is homomorphism with phi 7 equal to 6. Determine phi x, the image of phi, the kernel of phi. Let phi 1 equals to k, then phi x equals to kx, in particular phi 7 equals to k mod 6 is mod 15. Mod 15 equals to 6. So hence phi x equals to 3x. So I determine phi x. First step number 1. Number 2, the image of phi is 3 in 50, which is 3, 6, 9, 12 and 0. So friends, I find out the image of phi x. Now the kernel of phi. I have to find out the kernel of phi. To find out the kernel has ordered 50 divided by 5. 10 in Z50. So phi equals to 5 equals to ideal of 5, that is 5, 5, 10, 15, 20, 25, 30, 35, 45, and 50. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So we get curve phi is 10. Now we have to find out phi inverse 3. Phi inverse equals to 1 plus curve phi equals to 1 plus 2, 6, 11, 16, 26, 31, 36, 41, 46, 1. My total. Find the number of prime ideal of Z10. The positive divisors of 10 are 5. So the ideal 1, the positive divisors of 10, 1, 2, 5 and 10. So the ideals in Z10 are 1. Z10. So I equals to 0, 2, 4, 6, 8. Number 5 equals to 5. Order 10 equals to 0. So by inspection 2 and 5 are maximal ideal, are maxim ideal. So obviously they are prime, because I have already told that every maximal ideal is prime ideal. But converse is not true. Whereas 1 and 10 are find the number of maximal ideals of Z8, Z10, Z12 and Zn. So Z8 is ideal is 2, Z10 ideal is 2 and 5, and Z12 has the and maximal ideals are the form P, where P is prime, that divides n. Number 7. Let P, Q be distinct primes, then Z divided by Q has exactly 3 distinct ideals. Z divided by P square Q has exactly the 3 distinct prime ideal. Z divided by P square Q has 2 distinct prime ideals. Z divided by Q has unique maximal ideal. Generally, the ideal n are of the form D, where D divided by n. But how to describe all prime maximal ideals? Very conceptual. These are finite rings, and a prime ideal maximal ideal. Friends, I have already told that if ring is finite ring in a finite ring, maximal ideals divided by p square q j are those maximal ideals of J containing p square q j. Now, maximal ideal is prime, and a prime containing and a prime containing p square q must contain q or q or p, and p are maximal ideals. Maximal ideal. So there are exactly two prime ideal. It is also maximal ideal. Must remember. Find the number of homomorphisms from Z6 to Z12. So write no. the number of homomorphism and onto homomorphism, the number of homomorphism onto is equals to from Zm to Zn equals to GCD of m, comma. So find the number of homomorphism of Z6, Z6 plus Z12 is GCD of 6, 12. The number of onto homomorphism from Zm to Zn equals to phi n. Phi n means Euler totient function. Phi n equals to Euler totient function. Find when m greater than equals m less than equals to n and 0 if m less than n. Find the number of onto homomorphism Z6 to Z12. Z6 to Z12 as 12 is greater than 6. So number of onto homomorphism is 0. So this answer is 0. And the number of Z12 to Z6, Z12 to Z6, in here this is correct. It's 6. 6 is less than 12, so that we get onto homomorphism, number of onto, must remember, number of onto homomorphism is phi 6 equals to 1 minus 1 by 2 and 1 minus 1 by 3 equals to 6 into half into 2 by 3 equals to, now let's go to solve number 9. 9x to the power 5, 10x cube, 5x plus 15, and qx is equal to x cube minus x square minus x minus 2 be two polynomial elements in qx. then over Q. So friends, our Px equals to 9 to the power 5 plus 10 x cubed plus 5x plus 15, and P equal to P test. First we start P test. P equal to 2 as a prime number. So Px equals to x to the power 5 plus x plus 1, and it is irreducible over z2 x, as P1 equals to 1 and P0 equals to, that is, therefore it is irreducible over capital Q x. Now Qx equals to x cubed plus x square. Sorry, it is not plus. It is minus x square minus x minus 2, and P test by P test equal to 2. We get the value Qx equals to x cubed minus x square minus x. So it can be written plus x, which is reducible by 2. So our C option, Px is irreducible, but Qx is irreducible. This is correct, and all are wrong. Next, let's start to solve question number 10. Let G be a group with mod of G equals to 96. Suppose H and K are subgroup of G with mod of H equals to 12, mod of K equals to 16. Then H intersection K equals to E. H intersection K does not equals to E. H intersection K is E. So friends, know this formula. Norm of HK, order of H into order of K, order of intersection K. So friends, our G is, so HK, order of HK is subgroup subgroup of G. How can we say that order of HK group of G? Order of G equals to 96. That means 2 to the power 5 into 3. So 2 SSG, order of 2 SSG equals 32 order, and order of 3 SSG 3 order. Now 1 plus 2k is divisible by 3, so divisible by 3. This is the Sylow third theory. So friends, order of G is equal to 96. Suppose H intersection K equal E. Let G be Abelian. So HK because H and K both are normal subgroup of G. So order of G is equal to order of HK equals to 96, but order of HK equal to order of H into order of K, order of H intersection K does not equal H intersection K equals to E. So first option is not correct. So obviously second option is correct. And number 3, that H intersection K is Abelian. Now order of H K, so I use Lagrange's theorem. Lagrange's theorem as order of H intersection equals to E. So order of H intersection K divisible by order of H, and order of H intersection K divisible by order of K. because order of H intersection K is order of H intersection K is subgroup of H and K. So order of H intersection K equals to 2 or 4, and both are P and P square form, where P is prime. So hence H intersection K is Abelian. Number 3 is correct. Now friends, we are going to solve next problem. Now friends, let R be ring Cx divided by x square plus 1. Pick the correct statement from below. Dimension C R equals to 3. R has exactly 2 prime. R is UFD and X is maximal ideal of R. We know the fundamental theorem of algebra. If complex polynomial of degree n has exactly n so Cx divided by x square is isomorphic to C cross C equals to dimension C cross C R is 4. Dimension of C cross C is 2. If R is UFD, it implies R is integral domain. that is R is not integral. That implies R is not unique factorization domain. Now the definition of integral domain does not equal to 0 means no zero divisors. No zero divisors. Here 1 comma and 0 comma 0 equals to 0, which is does not equals to 0. Multiplication is 0 0. So it is not integral domain. So it is UFT. Now prime ideal. Let R be ring and ideal P, which is equals to R, is called prime ideal if for any A comma B belongs to R such that A dot B belongs to P. That implies either A belongs to P or B belongs to P. So this is the now 1 comma 0 cross 0 comma 1 equals to 0 comma 0 belongs to 0 cross 0, but neither 1 comma 0 does not 0 comma 0 0 cross 0, neither 0 comma 1 does not belongs to 0 comma nor cross 0. So they are not prime ideal. Now again R equals to C cross C. So 0, C and C cross 0 are, if we multiply both, then they are prime ideal. So number of R has exactly two prime ideal. This is correct. This portion is wrong. And X is a maximal ideal of, so this is correct. This is a 2 prime ideal because 0 cross C cross C cross 0, 0. So both R belongs to in this. So friends, I hope I can clear this concept. Now friends, we can say that the ring, again I want to discuss that the ring R equals to Cx divided by x square plus 1. Standard basis has the monomial monomial standard basis standard basis 1 comma x bar, since x bar square plus 1 bar equals to x square plus 1 bar equals to 0 bar in R, in capital R, where a bar equals to a plus x square plus 1 is the residue plus modular, is the residue of ideal by the isomorphism theorems for ring ideals in Cx containing x square plus 1 corresponding 1 to 1 with the ideals of the maximal of Cx are of the form x plus a, sorry, not x, x minus a with belongs to C. So friends, my dimension is 2. This is correct. And X is maximal ideal of R. This is also correct. Because we see that x minus a with a belongs to C. So it is a, and 0 is also belongs to C. So x is maximal ideal of C. Now Now friends, consider the function f(xy) equal to x square by y square, where xy comma belongs to 1 by 2, 3 by 2, and the derivative of the function at 1 comma 1 along the direction 1 comma 1 is. So friends, I have to solve directional derivative problem. Solution: if x comma y equals to x by y square, if x is equal to 2x divided by y, and fy equals to minus x square divided by y cube. So fx 1 comma 1 is equal to 2, and fy 1 comma 1 equals to minus 2. Now we discuss a theorem. This theorem is very important for remembering that theorem. If x comma y is differentiable function at the point p x0 comma y0, then the directional derivative exists in all direction, that is u equals to u1 comma u2, given if fx0 comma y0 equals to fx x0 comma y0 u1 plus fy x0 comma y0 u2. Now directional derivative of d 1 f 1 equals to fx 1 comma 1 into 1 plus fy 1 comma 1 into 1. So this value is 2 into 1 plus 2 minus 2 into 1 equals to 0. So my answer is 0. Next, number 13. Let sigma equal to 143,287 tau equal to 548 be cycles in S8. Express sigma tau and sigma tau the product of disjoint cycles. So sigma equals to 1, 4, 2, 3, 8, 4, 7, 5, 3 tau. Sigma tau equals to, this is where I will find out, 66715. Hence I have already taught how to multiply multiplications. You can watch my video, then you can get how to multiply permutations. 8 comma 7 and 5 4 8. So this can be written as 1 4 7 2 3 8 5. It can be written the true product of, and it is the tau comma sigma, not tau sigma. Now tau sigma equals to 5, 4, 8, 2, 1, 4, 8, 7, and it can be written, it can be multiplied with this 1, 4, 3, 5, 4, 6, 6, 7, 1, 8, 7. So it can be written as 1, 8, 7, 3, 5, 4. So I express as sigma tau and tau sigma as a product of disjoint cycles. So friends, now we start to solve another question number 14. Consider the function fz equals to sine pi by 2z divided by sine pi z. The f has poles at all integers, all even integers, all odd integers, all integers of the form 4k plus 1k. So friends, this problem is based on complex analysis. I will create another video where is the 50 problem solution of complex analysis. My next video I shall try to create, but I think that this issue is important. Why I try to explain this problem in this video, only one complex analysis problem. So let's start to solve. Fx equals to sine pi by 2 z into 2 sine pi by 2 z pi by 2 z. So I cut these 2 points. So I get 1 by cos pi by 2 z. So friends, if it is poled, so denominator equals to 0. So cos pi by 2 z equals to 0 equals to cos 2k plus 1 pi by 2. So z equals to, where k equals to plus minus 3 here, plus minus 2 etc, plus minus 1 0 etc. So we can say all odd integer, all integers is not possible, all even integers is not possible. All integers and all integers of the form 4k plus 1 where k belongs to z. Which of the following statements are true? Zx is PID, z x y y x comma y divided by y plus 1 is UFD. If R is PID, P is a non-zero prime ideal, then R by P has finitely many prime ideal, E has finitely prime ideal, and if R is PID, then any subring containing 1 is again a PID. So friends, let's try to solve number 1 solution. For 1, Zx is PID. One question, Zx is PID. This is wrong. PID, must remember one theorem I have already told. If F is field, then that implies Fx is PID. So friends, F is field, but Z is not field. So that implies Zx is not PID. It is UFD, unique factorization domain. So friends, I have already told what is. Now we will discuss point 1. So point 1, option 1 is option 1 is number 2, that Zx comma y, this y is capital Y friends, is UFD. So Zx comma y divided by y plus 1 is isomorphic to Zx. Let phi such that Zx comma y tends to Zx, then p x comma y tends to p x comma minus. Therefore phi is surjective, so card phi p x comma y belongs to Z x comma y, and p x comma minus 1 equals to 0. So Z x comma y plus 1 belongs to kernel phi, and px belongs to Zx. Ex comma y equals to qx comma minus y, and phi p x comma y equals to qx minus y minus 1. So in here you get that it is onto mapping r phi kernel phi equals to Z x comma y plus 1 equals to y plus 1. So by first isomorphism theorem, so curve phi equals to y. By first isomorphism theorem, first isomorphism theory, z x y y plus 1 isomorphic to z x. My first option is correct. Now we discuss that every non-zero prime ideal in PID is maximal. That is prime ideal R by P equals to field. That implies this is auto. Friends, if R is PID, P is non-zero prime ideal. Must remember, friends, P is non-zero prime ideal, so it is non-ideal. This ideal is maximal ideal. So R by P has finitely many prime and R is PID. If R is PID and P is non-zero prime ideal, so R by P has many prime. This option is correct. If R is PID, then a subring containing 1 is again a PID. This option is wrong. Counter example. Counter for 4. Counter example 1 belongs to Zx subset Qx. Qx is PID, but Zx is not PID. Number 16. How many self-inverse elements in D3H3 is where D3 is dihedral group? Self-inverse element. How many? Answer. Solution. H3 and D3 are isomorphic. Thus, we find part of elements of order in S3 which is 16, as there are total 3 cross 3 9 ordered pair. Pairs whose both elements order that is of the x comma y such as such that order of x equals to order of y equals to 2, where x comma y belongs to S3, three elements in which first element is identity and second is an element of that is of type X, where X belongs to S3 order Ax equals to 2 and 3 more of from x comma 1 and 1 is identity element of the group. Thus, total number of elements are 9 plus 3 plus 3 plus 1. Find all subgroup of A4. So find all subgroups of A4. The alternative group on 1, 2, 3, 4 is a group of order 12. There is no subgroup of order 6. The alternating group of degree 4 is the group of smallest possible order, in this case 12, not having subgroup of all orders divided the group order. So friends, you can say it does not hold it does not hold Lagrange's theorem. And list of subgroups. List of subgroups is first is trivial groups. Number 1. Number 1, trivial groups. That is isomorphic of trivial groups, trivial subgroups generated by double transportation in A4. That is 1, 2, 3, 4, 1, 1, 2, 3, 2, 4. This is the cyclic group of Z2. Similarly, B4 in A4. That is 1, 2, 3 and 1, 3, 2, 4. That is isomorphic to alien 4 groups. And number 4 is A3 is A3 A4. That is 2, 3, 4, 2, 4, 3, 1, 3, 4, 1, 4, 3. That is and 1, 2, 4, 1, 4, 2. And this value is 1, 3, 2. That is isomorphic to Z3. Number 5 is whole group. Whole group is all elements. Isomorphic to E4. So friends, I have discussed that only 6. Here you cannot get any of subgroups order 6. So it clean A4. A4 is the example of converse of Lagrange's. Converse theorem of Lagrange's. Converse of Lagrange's theorem. So I hope I can clear and is where the 3 cycle, that is this is so this is number order is 4. You see that this is order of isomorphic to Z3. This is the Sylow 3 subgroups. So friends, our topic, so order of A4 is equal to 2 square into 3. So they are cyclic of order 3. So there are 4 distinct subgroup of four distinct Sylow 3 subgroup. Sylow 3 subgroups. Okay, let's see that we have already told that these are Sylow 3 subgroups, means the number is, you will see 1, 2, 3 and 4. So, and because order of 4, a4 by 3 equals to 4. So friends, I hope I can clear this total concept of subgroup of A4. This is very important for every students. So now we start to discuss find all units zero divisors idempotent elements in ring Z6 cross Z. A comma B whole to the power n equals to a to the power n comma b to the power n equals to 0 comma 0. If and only if a to the power n equals to 0, and b to the power n equals to 0. So only pairs of nilpotent elements element of elements, sorry, not are nilpotents. We have two nilpotent elements we have two A and B. A and B such that a to the power n and b to the power n equals to 0. A comma b equals to 0. Thus all pairs of nilpotent. Thus all pair of nilpotent are nilpotent. 1, 2, 3, 4, 5. This is Z6. So nilpotent element and Z2 that is 0, 1, and the nilpotent element is nilpotent element is 0 square is equal to 0, and any other element we can get. Another is 2 square is equal to 4, 3 square is equal to 9, 4 square is equal to 16. Square here 4 cube anywhere we can't get. So my nilpotent element is 0, 0. And now idempotent element, because I get nilpotent element is 0, 0, 0. Now we discuss idempotent element. Idempotent element is a to the power n equals to a, b to the power n equals to b. 0 square is equal to 0, 1 square is equal to 1, and 4 square is equal to 4, and 3 square is equal to 3. So my idempotent element is 0, 0. Idempotent element is 0, 0, 3, 0, 4, 0, and 0, 1, 1, 1, 4, 1, 4, 0. So friends, I hope I get every point 1, 0. This is a total 6 element I get. So 0 divisors I have already find out. Idempotent element is also find out, and unit is unit. I hope I can clear the concept. Now we go discuss important note. Every permutation of finite set can be written as a cyclic or a product of disjoint cycle, commute, order of permutations. So let sigma is equal to sigma 1 and sigma 2 and sigma 3 and sigma n, where sigma 1 and sigma 2 and sigma n are disjoint cycle. Then order of sigma is equal to LCM of sigma 1 and sigma 2 sigma. So let's start that. Find the largest order of element in 7. So recalling that any permutation can be written as product of disjoint cycle. So this formula I just recalling that order of sigma is equal to sigma 1 LCM of this. So we can write disjoint cycle C is equal to C1, C2 up to CR. So I can write this way 1, 2 of order 2, 1, 2, 3 of order 3, 1, 2, 3 or 4 of order 4, 1, 2, 3, 4 of order 2, 1, 2, 3, 4 of order 5, 1, 2, 3 and 4, 5 is order 6, 1, 2, 3, 4, 5 is order 6, 1, 2, 3, 4 is order 4, 1, 2, 3, 4 and 5, 6 is order 2, 1, 2, 3 and 4, 5, 6 is ordered, and write this way, ordered 3. Order means this is the okay. So this way I just find out order. Similarly, I can write 1, 2, 3, 4, 5, 6, 7 of order 6. Another is 1, 2, 3, 4, 5, 6, 7 is order 10. Similarly, I can get 1, 2, 3, 4 5, 6, 7 is order 12. So similarly is 7. So the maximum possible order of an element in a 7 is 12. So this is my similarly question number 20. How can I find largest order of 10? So I have to find out the partition. So 9 plus 1 LCM of 9, 1 equals to 9. Similarly 5 plus 5 LCM 5, 2 plus 8 LCM 8, 7 plus 3 21, and 8 plus 2 I have already count. So 4 plus 4 tends to 4, 6 plus 12, and 3 1 2 1 3 4 5 6 7 8. So largest order of an element is 21. So please check the answer, and in here I get 12. So easily I can find out how I get, because I see that 4 plus 3 is equal to 7, and LCM of 4 comma 3 tends to 12. So identity is even permutation, transportation is odd permutation, product of two or odd permutation is even permutation, product of two is even permutation, cycle of even length is odd permutation, and cycle of odd length is even permutation. Number of subgroup group of order P in S equal to number of element of order divided by P minus 1. Number of cycles of Sn is equal to NCR R minus 1 factorial. Number of cycle subgroups of order M in Sn is equal to number of elements of order divided by phi m. So now let's start to solve this problem. Let G be a group of 2 cross 2 non-singular matrices under multiplication over the field Z3. Define a map F such that G R star, where R is group of non-zero real under multiplication, and if A is equal to mod of A, then find out phi car F. So let G be a friends. I mistook in here. What is my mistake? My mistake is largest element is not 21. There is another way. 2, 3 plus 5. So LCM can be written this way, that 2, 3, 5 equals to 30. So it is largest order of element in S10. Now a solution, I have already told that let G be a group 2 plus 2 non-singular matrices under multiplications over the field Z3. Define a map F such that G tends to R star, where R star is group of non-zero real under multiplications, such that if A is equal to mod of A, then order of car F is. Number 1, a member of is a X A C B D with A comma B comma C comma D belongs to Z3 and AD minus BC equals to 1 of mod 3 for any A does not equals to 0 and any B C okay. So D equivalent to 1 plus BC divided by A mod modulus 3. 3 2 plus 3 plus 3 equal to 18 choice. If A equals to 0, then BC equals to 1. So B equals to, that implies B equals to C equals to 1. Or B equals to C equals to 2. This makes 6 additional So total is 18 plus 6 is equal to 24. So friends, this is the another way. There is also another way. If A is equal to mod of A, so by the fundamental theorem of homomorphism, if such that A tends to get A, so my RF is equal to SL in capital F. SL in capital F is equal to 3 square minus 3 as F is equal to Z3, F is equal to Z3 and N equals to 2. So 3 square minus 3 and 3 square minus 1 divided by 3 minus 1. So this value is 6 into 8 divided by 2. So this value equals to 24. 8. RF is equal to SL in F. SL in F means date A equals to 1. So this way you can find out this problem. Now next is such that Z12 tends to Z12, then find the number of inner automorphism. Z12 is cyclic, that implies Z12 is Abelian group, that implies if G equals to ZG, center of G, capital G, we know that G divided by ZG is isomorphic to inner group. So mod of inner group is equal to order of G divided by ZG. So this value is 1. So my answer is 1. Now next we will discuss that number of conjugate classes of a non-Abelian group of order 125 is, hence a group of order p cube where p is prime have p square plus p minus 1 number of conjugacy, number of conjugacy plus so p to the power n where p is prime order of g equals to p to the power n, then equals to p to the power n minus 1 plus p minus 1. Property of mod of g dash equal to mod of zg. P cube is equal to p plus summation plus of conjugacy x g such that g x is index, so it is p plus p cube minus p divided by p equals to p plus p square minus 1. So my value is, let p equals to 5, so it is 5 plus 25 minus 1 equals to 29. This is my answer. That is 29. Let H and K be the two subset 144, and if the order of H is 24 and order of K is 36, then the order of the subgroup H intersection K is, so H intersection K equals to X belongs to G, X belongs to capital H, and X belongs to K, and H is 24 order of H, order of K equal to 10 times 2, 36. So the order is order of H comma K divisible by 24 and order of HK divisible by 30. So order of H comma K equal to GCD of order of H comma order of K. GCD of 24 comma 36 equals to 12. So the number of all subgroups of the group Z60 plus modulo 60 is, you have to find out. Two square into 3 into 5. So the number of subgroup divisor is 60. So divisor the number of divisors equals to 60. Oh, sorry, the number of divisor is 2 plus 1, 1 plus 1, and 1 plus 1 is equal to 3 into 2 into 2 is equal to 12. So my answer is 12. Answer is 12. G be a cyclic group of 24 order. The number of a group of isomorphism of onto itself is group of order 24. So number of group isomorphic is equal to phi 24 is equal to 2 cube into 3 is equal to 1 minus 1 by 3, that is equals to 8. So my answer is next. The number of group of homomorphism from the cyclic group Z4 to the cyclic group Z7. So result, important result, Zm to Zn GCD of M equals to GCD of 4 equal to 28. So my answer is, sorry, GCD of 28 not, it is value is this value is 1. So my answer is 1, not 8, 1. 1 is next. The order of 2 in the field Z29. Result, solution, result, result is that 2 to the power m equivalent to 1 mod 29. So therefore 2 to the power 5 is equal to 32 mod. So this will become 3. After that 2 to the power 5 whole cube is equal to equivalent to 3 cube mod of 29. So equals to minus 2 mod 29. Now 2 to the power 15 to whole square equals to equivalent to minus 2 whole square mod of 29. 4 mod 29 and it can be written as 2 to the power 28 into 2 square equivalent to 4 mod 29. After that it can be written 2 to the power 28 equals to 4 by 4 mod 29. So my answer is 2 to the power 8 to the power 28 means order is to 28. Next, question number 29. Let G and G dash be groups and let phi psi such that G to G dash be group of homo which is surjective onto. Which of the following statements are true? Number A, G is abelian, G dash and it is abelian. G is cyclic, G dash is cyclic. N is normal subgroup of G, I is normal subgroup of G dash. Group of homomorphism phi such that G tends to G dash and psi A comma B equals to psi A into psi B for all A comma B belongs to G. If G is abelian, that implies G dash is abelian. So this statement is true. Phi E is equal to E dash abelian group. Let x comma y belongs to G, then xy equals to yx as a abelian group, abelian group. Phi xy equal to phi x phi y and phi yx equal to phi y into phi x. So G dash is abelian group. If G is cyclic, that implies G dash is cyclic. So there G is equal to x to the power n does not equals to x belongs to G. Equals to order of x. Example. So G is cyclic, that implies G dash is cyclic. I think it is true, but I need to check this portion. That's why I will not solve this portion. I have to check that it is correct, false, or check. In my next video, I will try to solve this problem. Let G be the group of all symmetries of the square. Then the number of conjugate classes in G. So G be the group of all symmetries of the square, then G equals to D4, and the number of conjugate classes in G is D4 is equal to 5. So my answer is 5 is my answer. Let G equals to S3 be a permutation group of 3 symbols S3, and then G is isomorphic to a subgroup of cyclic group. There exists a cyclic group H such that G maps homomorphically onto H. So friends, in my answer, this option is not correct, false, because we can, here is that, because phi such that Z2 tends to, sorry, it can be written this way, U8 tends to Z2. Z2 is cyclic group, but U8 is cyclic. So this is not mean that G dash is cyclic, and this portion I have to see, I have to check. Let G equals to S3 be a permutation group of 3 symbols, then G is isomorphic to subgroup of G equals to S3 tends to Q plus. Now I write that trivial fx equals to 0, that is identity for all x belongs to, and non-trivial fx does not equals to 0 for all x belongs to G. A finite order element can infinite order element. A finite order element can never map to infinite order. So option 4 is wrong. There exists a non-trivial group homomorphism from G to additive group of Q plus rational, because S3 is finite group. In here S3 is finite group and Q plus 3 is finite group, and Q is infinite group. So So it is not possible. G is product. I use G is product of finite product of cyclic groups. This option is wrong because I use fundamental theorem of finite Abelian group if G1, G2, G3 up to Gn are finite group, then finite groups, then G1 cross G2 cross G3 cross dot 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 up to cross Gn is isomorphic Abelian group. A finite Abelian group. So Sn is S3 is non-Abelian group. G is product of cyclic groups. This is wrong. There exists a cyclic group H such that G maps homomorphically onto H. Let H equals to Z2 equals to 0, 1, plus 2 is cyclic and is a finite group. So it is finite group. This is the mapping I 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. So friends, this is the number 1, 2, 3, 4, 5, 6 element, and this is 0 and 1. We easily see that a map is possible. This mapping is possible. There is a mapping onto map. So there exists homomorphically onto H. This is possible. That's why friends, this is also, you can I give one example that in here this option is also wrong. That which options I have to 1 minute. This question that G is cyclic and G dash is cyclic. This is high such that 2 tends to S3. Sorry, S3 comma Z2. Then you can say S3 comma Z2. So friends, from these questions we have learned that this kind of question S3 is not Abelian, non-Abelian group, but Abelian group, Abelian cyclic group. So this is not that if G is cyclic, then G dash is cyclic. That implies this is not possible. If G is Abelian, G dash is Abelian. This is possible. Okay, but I will check and I will inform that this is correct or not. G is isomorphic to subgroup of a cyclic group. G is isomorphic to a subgroup of cyclic group. This option is not correct. Now we are going to solve the next problem. Which of the following subgroups are normal in GLN-C? H equals to A belongs to GLN-C. A is upper triangular. H equals to A belongs to GLN-C. A is diagonal. And A belongs to GLN-C. A is dead. A equals to 1. So solution. So first option is correct. Wrong. Second option is wrong. Third option is correct because this is SLN F. SLN F is the card F of GLNC, and it is normal subgroup. So I will solution explanation we need. GLNC, we have to know normal subgroup. Okay, GLNC, A is upper triangular. This is true or not? We have to learn. A belongs to GLNC equals to H. This is normal subgroup or not? At first, we have to know the definition of normal subgroup. What is normal subgroup? H less than equals to G. Then H is normal in G if H belongs to G. H belongs to capital H belongs to capital G, such that GH inverse belongs to capital A. Now A is upper triangular. So what is the meaning of upper triangular, friends? Now we will check. Capital H equals to 1 0 0 1, sorry, not 1 0 1 1 and 1. This is my triangular, right? Triangular, and small g equals to 1 1 0 0, sorry, 0 no, 1 1. So if we apply G inverse, we see that 1 1 1 into 1 into 1. So we see that it is does not belongs to H. So H is not normal subgroup of G. Number B option is correct. So A is diagonal if for number B, for option B, if A is diagonal, if H is diagonal matrix, then get H, its small h is 2 0 0 1 and G equals to 1 belongs to GLNC, but for option C it is you can get GH. G inverse is also H, because of date of G into date of H, because determinant is, we can write determinant as a product form. So date of H equal G, G inverse equals to 1. So correct. This is the subgroup of normal in GLNC. Next friends, we have to find out the basis of Q root 2 I comma such that Q. So friends, our next problem, find the dimension of Q root 2 comma I such that Q. So Q root 2 comma I can be written as Q root 2 or Q such that Q root 2 equal to B such that A comma B belongs to Q, and base of the 2 equals to B1 equals to 1 comma root 2. Dimension of Q root 2 comma Q equal to 2 root 2 comma I such that Q root 2 equals to Q root 2 comma I equals to Q root 2 I. Now formula is that K such that if K such that E and E such that if. Here K is the field and K such that E equals to this, and E such that is the F is the field, so E is middle portion. So in here K such that E U root 2 equals to, can be written A plus IB such that A comma B belongs to Q root 2 Q root 2, that is 2. So Q root 2 I such that Q can be written as Q root 2 into Q I. Sorry, it is Q root 2 Q QI such that Q. Sorry, here Q root 2 comma I such that Q. So this value is 2 cross 2 equals to 4. Question number 34. Let fx belongs to zx be monic polynomial, then the roots of f can belongs to z always belongs to this, and it always belongs to this. All are wrong. Now I will discuss that fx this option is also right. fx is monic polynomial. Fx is monic polynomial. Coefficient co fx. So monic polynomial coefficient is always integer. So for example, fx is equal to x square plus 1. So the roots of polynomial is never rational number. So can belong to Q minus Z. This is not possible. Can always belongs to Q C minus Q union Z. This is not possible. So possibility is only this, because in here you see that R minus Q is equal to irrational union Z means real number. So here it can be belongs. As Z is integer, so zx is U FT, unique factorizations domain. Now question number 35. Let f such that z by 4z, z by 6z be the function such that fn is equal to mod n mod f 4 n mod 6. So then 0 mod 4, 3 mod 6 is in the range of f. This problem I have to solve. So z by 4z equals to z4 and z by 6z equals to z6. So now we have to solve f 0 comma 0 equals to f0. So because n is mod 4 and n is mod 6, so obviously it is correct. And f3 is equal to 3 comma 3, f1 equals to 1 comma 1, f2 equals to 2 comma 2. Similarly, f4 equals to 0 comma 4. And f 1 comma 5, and if we get 2 comma 0, and f6 to f7 equals to 3 comma 1, f8 equals to 0, 2, f10 equals to 2, 4, f9 equals to 1, 3, f10 equals to 2, 4, f12 equals to. So friends, we don't need to do so many work, but I just try to explain how I can get. So Csir Net F24Z, this is wrong, and image of F has exactly 6 elements. This is also wrong. A mod 4 and B mod 6 is an image. This is correct, and this is, I hope you can understand. Next problem is very interesting. Chinese remainder theorem. So at first read this problem. Find the smallest positive integer which give the remainder 1, 3 and 2 when divided by 4, 5 and 7 respectively. X is equal to 1 mod 4, 2 mod 17 and x equals to 3 mod 5. Or find the smallest positive integer which give the remainder 3 in each one when divided 5, 6, 7, 7. Okay. Let's try to solve this problem. So friends, this problem is Chinese remainder theorem. I will solve the remainder, and this question is find the smallest positive integer which give the remainder 3 in which one with when divided 5, 6 and 7. So when 5, 6 and 7, then it is LCM of 5, 6, 7 plus remainder 3, 233. Number 1. Number 2, 1, 2, 3 when divided by 3, 4, 5 respectively. So LCM is equal to 3, 4, 5 equals to 60, and minus 2 equals to 558. How can I get? How I get 2? Because 3 minus 1 equals to 2 and 4 minus 2 equals to 2 equals to 2, so it is 58. 2, 3, 4, 5 when divided by 3, 4, 5, 6. So friends, again we see that 3 minus 2 equals to 1, 4 minus 3 equals to 1, and 4 equals to 1, 6 minus 5 equals to 1. LCM of 3, 4, 5, 6. LCM is 60. 3, 4, 5 and minus 1 equals to 59. So I hope I can clear. Now I will solve this problem. Next problem. Next problem is question number 36. Chinese remainder theory. Let M1, M2, MR denotes R positives, integers, are relatively prime in pairs and let A1, A3, AR denote R integers, then the congruency X equivalent to I equals to 1, 2, 3 up to n have common solution any two solution are convenient, mod m where capital M equals to m1, m2, mn. I don't need to prove this theorem because this theorem can be also proved. So let's try to solve our problem. X equals to 1 mod 4, x equals to, sorry, this is not 1, this is 7. So 2 mod 7 and capital A, 3 mod 5, so A1 equals to 1, A2 equals A2 equals to 2, A3 equal to 3, M2 equals to 7, M3 equals to 5. So capital M equals to 4 into 7 equal to 140. So capital M1 equal to small m1, okay, capital M by small m1 equals to 140 35, m2 equals to capital M divided by m2, 140 divided by divided by 7 equals to 20, and m3 equals to capital M divided by m3 equals to 140 divided by 5 equals to 28. So I find out capital M1, capital M2 and capital M3. Now I can write 35x equals to equivalent to 1 4. Another is 28x equals to 1 mod 5. 20x equals to 1 mod 7. So 0 equivalent to 36 mod 4. So this is 1 and this is 2. 1 minus 2 equals to 35x is equal to minus 35 mod mod 4, and this is 0 equivalent to 29. It is better, it is 55 is better. 55 mod 5. So x is equal to minus 1 mod 4. So x equals to 3 mod 4. Similarly, 28x, this is 1 and this is 2 plus. So this portion is x equivalent to minus, so 21 mod 7. 21 mod 7. So subtracting this, we get 0x equal to 20x equivalent to minus 20 mod 7. So x equivalent to minus 1 mod 7. So x equivalent to 6 mod 7. So x3 equal to 6 and x is equal to mod x2 equals to 2, x1 equals to 3. Capital X m1 x1 a1 plus m2 x2 a2 plus m3 x3, sorry, both are small, x1 x2 x3. So 35 equals to into 3, 28, 2 into 3 plus 20 into 6 into 2. So that is, so 5 to equivalent 93 mod 140. So friends, I hope Now we will solve next problem. Find all prime maximal ideals Z3x plus Z5. Solution. Since Z5 is a field, zero is the only prime maximal ideal of capital Z5, a non-zero ideal I of Z3x maximal or prime ideal of Z3x if and only if I equals to px for some irreducible polynomial dx of Z3x. Hence, 0 plus Z5 is a prime ideal of Z3x plus Z5x, Z5 and px plus Z5, where px is an irreducible polynomial, where px is an irreducible polynomial of Z3x and x plus 0 are both prime and maximal. 3x plus Z5. Now find all prime prime maximal ideals of Z3x, x plus 2 whole cube, x plus 1 whole to the power 5 plus Z12. Let I equals to x plus 2 whole cube, x plus 1 power 5. By an we can conclude we by I as 1 divided by I are the prime hyphen maximal ideal prime and maximal ideals of Z5x by I. We conclude 2Z12 and 3Z12, 3Z12 are the prime maximal ideals. Ideal of Z12 prime ideal is x plus 2 divided by I plus Z12 Z12 and plus I divided by I plus Z12 Z5x plus 2Z12 Z5x divided by I divided by I 3Z12. Those are they are they are all maximal ideal. Find a maximal ideal of Z12x. Since 3Z is a maximal ideal of Z12, we can conclude P equals to fx belongs to Z12X such that F0 belongs to 3 Z12X is a maximal ideal of Z12X. Let G be a group of order 200, then the number of subgroups of order 25 is solution. Order of G equals to 200 equals to 25 into 5 square plus G has a 5 Sylow subgroups of order 25. Number of 5 Sylow subgroup of order 25 equals to 1 plus 5k, where k is 0, 1, 2, 3, dot any number. P divides since P divides order G equals to since T is so that implies 1 plus 5k divides k equals to 0, so number is 1 by theorem. Let S10 denote the group of permutations on n symbols So the number of element is 10, commutating the sigma 13579 are given tau belongs to S10. The condition that tau should commute with sigma is equivalent tau sigma tau inverse is equal to sigma, but tau equals to 1, tau 2, tau 3, tau 7, and tau 9 equals to 1, 3, 5, 7, 9. So tau 2, tau 4, tau 6, tau 8, and tau 10. Freely chosen among 2, 4, 6, 8, yielding 5 factorial possibilities. Thus, there are tau are entirely determined. Thus, there are 5 into 5 factorial 600 possible permutation. Again, I repeat, once tau 1 has been chosen from among 1, 3, 5, 7, 9. The remaining values of tau entirely determined. Next, find an element of order 12, Q8 and S3. So I and 1, 2, 3. Number 44. Find an element order 6 in exponent that is GCD of and 9 equals to 6. So this value 1, 2, 3, 4 and 3. Determine find the element of order 6 is D4 into D4 has 5 elements of order 2. D4 has 5 elements of 2 and S has 2 elements. So 10 elements ordered 6. So my answer is 10. So the order of 8, 10 in Z18 and Z12. So now this problem is very interesting. So we 8 is 18. So how can we get? If we multiply with 5, then it is equal to 90, and so friends, we will solve this problem. This problem is solved. This problem we will solve very soon, but discuss one problem point. This problem this problem is this problem is true. Why? A group homomorphism maps conjugate to conjugate. So that's why it is correct. Now we solve number 47. Find the number of elements of order 20 in the multiplicative group Z star 100. So order of 7 class of 7 belongs to Z star 100. So 7 to the power 4 equals to sorry 7 to the power ln to 1 modulus 100. So order of box 7 equals to 4 by Chinese remainder theorem by Chinese remainder theorem, Z star 100 isomorphic to Z star 4 plus Z star 25. An element of the latter subgroup A, B has order is LCM of A, B. Mod. So, so mod of A and mod of B equals to 20 and mod of B equals to 20 if so Z star 25 Z 20 if isomorphic to Z. Sorry, this is not. This is 20 equals to 8. How? Because you see that 20 into 1 minus 1 by 2 into 1 minus 1 by 5. So this would become 10 into 4. So this is 8. Groups have high n elements of order n. Cyclic groups have high n elements of order n. Hence, option 2 for a Z4 star. So my total number is 16. Now we discuss important note. If P is a prime number, then any group of G of order P square is abelian. Let F such that G tends to E, then kernel phi F is normal subgroup of G. And if G by ZG is cyclic, then G is abelian. Let G be a non-abelian group of order Pq, where P is prime number. There are non-abelian groups of order less than 21. A group homomorphism from a simple group is injective. This does not mean that F is injective, since the kernel of phi must be normal subgroup. The kernel can only be trivial on G. If the kernel is trivial, phi is injective. Otherwise, if kernel is G, then phi is 0. If the kernel is G, then phi is 0 map and is not injective. There are unique non-abelian group of order 21. Let G be a non-abelian group of order PQ, where P is prime number, and let G be a group of order PQ, where PQ are prime and P less than Q, and P does not divide Q minus 1, then G is cyclic. The union of two subgroups is subgroup if and only if one contained in other. If every element of group G, composed is its own inverse, then G, composed is abelian. A inverse will be B inverse, the alternating group. The alternating group is let x1, x2, xn be independent variable, and let del be the polynomial such that del equals to 1 less than equals to I, j equals to less n, xi minus xj. The product of all terms xi minus xj for I less than j. For example, when n equals to 4, then del equals to x1 minus x2, x1 minus x3, and x1 minus x4, x2 minus x3, x2 minus x4, x3 minus x4. For each sigma belongs to Sn, let sigma act on del by permuting the variable in the same way the permutes their indices. For example, if n equals to 5, sigma is equal to 1, 2, 3, 4, and then sigma del is equal to x2 minus x3, x2 minus x4, x2 minus x1, x3 minus x4, x3 minus x1, x2 minus x1. And then we have following. Let R be commutative ring with unity and I be ideal in R. Then we have following. R by I is integral domain. If I is prime ideal, R by I is a field. If and only if I is a maximal ideal in R. So now we will solve question number 48. This is very interesting. Let A be the reflection of the plane R square in the line y is equal to minus x. Find the matrix of A in the standard basis H is equal to A2. So A be the reflection of the plane R square. A be the reflection of the plane R square. This point is markable. Y is equal to minus x and x equals to E1. So E1 equals to A1 comma 0. That implies 0 comma minus 1. Similarly, E2 is equal to A 0 comma 1, that is minus 1 comma 0. So my matrix is A is equals to 0 comma minus 1 minus 1 comma 0. So I find out the matrix. This is my answer. My answer is this. Next, consider the polynomial x cube minus 2 equals to qx and q2 to the power 1/3 such that q So friends, before this question, I will solve question number 50. Consider the polynomial px into x to the power 4 in the ring qx of polynomials. The variable x with coefficient in the field q of rational numbers. Then the set of zeros of px in C from group under multiplication. This option is wrong. This option is wrong. This option is correct. So how can I solve this? Because px equals to x to the power 4 plus 4 equals to 0 minus 4 power 1 by 4. So it can be written e to the power I pi by 4 root 2. So equals to q 1 plus I 1 minus I and minus 1 plus I into 1 minus I. So it can be written this way, that q1 plus I equals to qi, because in here you can get 1 plus I 1 minus I minus I 1 minus I 1 minus I. So px and you see that qi number d is easy, that the degree 4 over x is degree 4 over q. This I hope I can. Now we will solve next problem. This is the last problem, that consider the polynomial x cube minus 2 belongs to qx. So x cube to the power 1/3 such that q. So x cube equals to 2. So x equal to 2 to the power 1/3, 2 to the power 1/3 omega, 2 to the power 1/3 omega squared. So q to the power 1/3 such that q equals to a 2 to the power 1/3 b plus 2 to the power 1/3 c. So this answer is 1. I hope I can clear total. So friends, x cube minus 2 equals to 0. Let p test p is equal to 2, then p divisible by minus 2, p does not divisible by 1, and p square does not divisible by 2 by minus 2. So by Eisenstein theory, Eisenstein criterion by Eisenstein criterion fx is irreducible. Fx is irreducible over q. So x cube equals to 2. So equals to 2. So x equals to 2 to the power 1/3. So the problem is q 2 to the power 1/3, q 2 to the power 1/3 equals to basis is 1, 2 to the power 1/3, and 2 to the power 2 by 3, to the power 1 by 3. So qx divided by x cube by 2 minus 2 isomorphic to q into 2 to the power 1/3, and this value equals to 3. Thanks for watching.